So I still have 5 minutes. I still want to continue, right? I have this example, yes and no question. It is also in my book, right? So what is a basis state? A good analogy is, let's say a boy, he likes a girl, and you don't know if she likes you or not, right? So what is the state of the girl? It must be yes plus no, right? I guess you guys, some of you have this experience like me. Then what happened? Well, eventually you need to do a measurement, right? How do you measure? Also, exactly. When you do the ask a question, what happened to the states of the girl? When you do measurement, collapse to what? Yes or no, right? The problem is that you don't know whether it's yes or no. And in most of the story, the answer is no, unfortunately. Right? That is like this. That was the basis state. But it collapsed to no. The state of the girl becomes no. But I say it, I can write more. The state of the girl after saying no is, of course, no. But however, it doesn't prevent you from approaching her, say that, hey, I have EE 255 project. Do you want to partner with me? Now, the point is, if you're not a bad guy, right? There's a chance she will say yes or she will say no. Correct? Yeah, I don't like you, but you're a good classmate. Why not? Right? So the states of no in the affection basis, what I say, right? The girl, it is still the same state, but you're in the affection basis, it is collapsed to no state. It can be a linear combination of yes for the project or no for the project. Make sense? So here I want to show you that for the same state, you can represent in 2 different bases. I'm going to show you more mathematically later. Okay, good. Then the state will become yes, P, right? It will collapse to yes, yeah, I want to do project with you. Before that, when it is no, if you measure it again, quantum mechanics tells us what? When you collapse to the basis state 0, you measure again, what do you get? 0. You measure 1,000 times, it's still 0, right? Same for the girl. You ask one, do you like me? No. Do you like me? No. Tomorrow, 10 years later, 100 you still ask to measure? Still no, right? But now, I make it into another basis. Do you want to work on a project with me? Yes. Okay, so her state is project yes now. Okay? But this project yes can be a linear combination of this affection basis yes and no again. I will show you. Because they are not compatible with each other. Okay, now the analogy start breaking down, but just trust me, right? It is like this. Now, if I ask her again, do you like me after this project? Actually, she might say yes. But in reality, it may be true because I impress her. I'm so good, right? I'm so responsible, right? And now she changed her mind, right? I want you to think about this analogy, how it maps to the concepts I'm going to teach you later. The change of basis, the basis, superposition, orthogonality, which we will say, because if yes and no cannot exist at the same time, okay? That's why they're orthogonal. Wave function collapse. This will not be in the exam, but try to compare to the analogy. That will improve the understanding of the concept. Many parts are wrong. I just told a student today. For example, I cannot prove Heisenberg uncertainty principle from here. Right? Later, you tell me why this one does not contain Heisenberg's uncertainty principle. Right? You have not learned it, you will learn it later. So let's go to the real math, okay? I don't have the cheat sheet with me, but I think I remember what I want to say. Vector space, we start with vector, right? So for example, we know very well I have this x-axis, y-axis, right? I have a vector here. And this is 1, 2, 3. This is 1, 2. This vector E, how do we represent it? Well, I can say this is 3x hat plus 2y hat. Do you agree? Okay. No? Yes. What if I write it in this way? 3x plus 2y. Do you agree? Any problem that I write in it this way? Do you feel uncomfortable? A little bit uncomfortable, right? But why do you want to be uncomfortable? It's just a notation. You know, if I write that 3 square plus 2 triangle, as long as you know the square means the unit vector x hat, and the triangle means the unit vector y hat, we are communicating with the exact information. But that's why I don't need you to learn linear algebra at the beginning. Just take the bracket notation, x, y. Trust me, this is just a notation. You know this is like the oxygen atom I told you. You even don't know what is inside the oxygen atom. It's a stuff, a basis, the basis. So if that is the case, what if I write it in this way? Is there a problem? No, right? Yeah. 3 squared plus 1. Oh, okay. Now I have not gone to unit vector yet, just a regular vector. Not quantum mechanics, no quantum computing yet. Just a regular vector in the space. Yeah, good question. Okay. So I know time's up. The final thing is that I hope you understand 3, 2 is okay. As long as you know this 3 represent x hat. This 2 represent y hat, or a square or a triangle, whatever. Okay? So let's continue next time. Go back to the most basic thing we learned last time. I did not have time to finish the vector space. Let me remind you again. Everything in quantum computing, right, or linear algebra, right, they represented by a vector. So here is very simple. I just have a vector in the 2D space. But it should not stop you from extending all the concept to something you cannot see. Okay, so that's why we start with a 2D space and to remind ourselves some of the basic thing. This is a vector. I put in this system x and y. X has a unit vector x hat, y has a unit vector y hat, right? So I say, what is the value of v? Right? What is the vector? How do you represent it? It has some basis, as I told you, right? We learned before basis. Just like one egg is the basis of how many eggs you have. Right? I ate 2 eggs this morning. 2 and then 2, 1 egg. Right? Each 1 egg is the unit. Okay? Like how many people in my family? Each person is the basis. I have 4 people. Now, you even don't need to worry about what are those people in my family, because what you're interested in now is just the basis spanned by the people, by the person. Okay? So, similar here, for this V, it now has 2 bases. Basis vector, I should say, sorry. It's a whole basis, but the basis has 2 basis vector, x hat and y hat. And you are already used to this already, right? V is a vector is equal to 3 x hat plus 2 y hat. Is this okay? Very familiar? In that case, what is x hat? Yeah, you know it's a unit length on the x-axis. But it really doesn't matter, even you don't know this, right? Just like 1 egg. I say I ate 2 eggs this morning. 2, 1 egg. But you did not know what egg. Is this a chicken egg, duck egg, or whatever egg, right? So this one is just an abstract. We take it for granted. So I can write it as x hat, and since even the content is taken for granted, the name can be anything also, right? So I write it as this Dirac Braket notation. I want you to get familiar with this ASAP. X and Y. Is this okay? Nothing special again. If that is the case, if I have a contract with you, we talk to each other, we say, from now on, let's call x hat as square, and then y hat as the triangle. And then when I communicate to you, where are you now? Oh, I'm at 3 square plus 2 triangle on the campus with the origin in the engineering building, right? This one, is it confusing? It's not confusing, right? So if this is the case, I can also write it as 3, 2. As long as we understand the 3 represented, it has 3 units of the first basis. Now I call it the first basis, not just that it's x hat, right? For me, what I care about is more like this is the first basis vector. Right? And this is the second basis vector. I even don't need to know the name, whether it's x hat, y hat, triangle, or whatever. I know that in the system, in the space, I have basis vector. And I have the freedom to just order them. First, second, third. But once I order, you need to follow this order in all the calculation. Don't mess up. Okay? And that's it. 3 represents the 3 units of first basis. 2 represents the 2 units of first basis. Okay? Now, if this basis is like this, then I can also, for exactly the same vector in what I'm showing here, I can have another basis also. I call it y dash, right? X dash. And see how I do it. I actually decided to call this length as 1 unit. This is 2, this is 3, this is 4, this is 5, and this is 6. And similarly, this is 1, this is 2, this is 3, this is 4. For exactly the same vector, I want to represent in the new basis. Can you tell me, what is this?
6x plus 4.
6x hat dash, let me call it dash because it's a new system, right? Plus 4y hat dash. It's just a different basis. Now it's just like, instead of eating 2 eggs this morning, I actually ate 12 eggs. And I can tell my mom I ate 1 eggs. I can tell my father I ate 1 dozen eggs. They are exactly the same, but different bases. So when we describe the quantum system, the most important thing is to understand what basis I'm talking about. Okay? I say this house live 4 families. Fine. Assume each family has 3 people. Then I know that there are 12 people. I can also say this house live 12 people. Right? Then you are still talking about the same residents, but you have different number, different bases. So how do I write this? Well, I also can write is 6x hat dash, right? It's up to me. This time I have the hat 4y hat dash. It doesn't matter, right? Now I don't want to play with triangle. We grew up already. I just put this. What is the meaning of 6 in this case? Thank you. It means I have 6 units of x hat dash or 6 units of first basis vector. But this first basis vector is different from the first basis vector here, right? This is a different basis vector because I'm using a different basis. Although you may say, well, they are just 2 times of each other. But remember, they can be at angle to each other also. We have not discussed that. And it can be a hyperspace which you cannot touch, you cannot see. Okay? Yeah. Mm-hmm. Yeah. It's still okay. I will talk. Okay. Let me finish this. Y hat second basis vector, right? So he said that, can I just do this? 2 times 3, 2. Absolutely okay. But still this one has nothing to do with this one. Okay? At most you just say that I realize that the basis is 2 times of this, so see that I can factorize 2. But if you did not know about this basis, this is just a notation. I take a common factor out, right? This still saying that I have 2 times 3 first basis vector and 2 times 2 second basis vector, and add them together is my vector. Okay? Some of you feel this is super simple, a waste of your time, right? But doesn't matter. Yes.
So when doing a homework question or any questions,
It doesn't matter. You can factorize it or not. You just do something makes sense. That will be okay. Right? Good. So we know what is vector. What is vector space? Very fast. Then I will go to some very important operation called inner product or the dot product. Okay. Let's look at this example. So I have another coordinate system. Again, we draw in 2D. But imagine, this can be something you cannot see. Imagine you are a creature, only can run in the one-dimensional. You cannot understand what is the meaning of two-dimensional space, right? So this can be a hyperspace for me if I'm just a one-dimensional creature. So here I have X, here I have Y. And particularly, I have a vector, which is this long. This is V. And here I have square root 3. So if you remember trigonometry, when this is 3, and then this is 1, this is 30 degree. Okay? You just trust me. If you forgot, right? Trust me, because that's not the purpose of this class. Now I can have also another vector, which is like this. Okay? So I should call this V1 and this V2. And this vector has a unit of 1 here. So what is the angle between these two vectors? What's the angle between these two vectors here? 15, because this is a 45 degree, right? Because it both is 1, right? Okay, so let me write it down. Now you are so good now. Can you tell me, how do I represent V1? What is this? Square root 3 x hat plus 1 y hat. Okay, we not want to use column form because this is quantum computing class, right? So how do we write it? Square root 3, 1. Okay, not 3 over 1. Square root 3, and then just a space, 1. Okay, square root 3, 1. It means I have square root 3 units of first vector, first basis vector, x hat. I have 1 unit of second basis vector, y hat. Okay, good. How about V2? How do I write it? Thank you. Yeah, thanks for all your help. X hat, Y hat, because my purpose is that you learn in the class. I don't want you to go back to study, right? Learn everything in the class. 1, 1. That's it. 1, 1. Okay? What is the dot product? I wonder if you remember. The so-called dot product is also the so-called inner product. And what does it do? If you remember, that would be great. If you forgot, then let me remind you. What it's trying to say is that you project one of the vector, for example, I project V2 onto V1 and find their overlap. And this is nothing but just like you have a sun perpendicular on top of the V1, right? Perpendicular, you project a light perpendicular to V1 like this. Some lights coming in. And you form the shadow. That is called projection. Now, projection is a very important concept, very difficult one. One of the important projection is measurement. What is measurement? Measurement is actually you randomly project the state into one of the basis states. Remember the coin spinning? When I stop it, you project this superposition state into one of the basis states. The only problem is that we don't know how it projects. We only know that it will do it randomly, but statistically, it has some rule, right? Remember? Right, so projection is very important, okay? So we learn in basic trigonometry. If you forgot, no problem. I give you the equation. I hope you can remember. V1 times V2. What is the meaning of this 2/9? Magnitude, thank you. And then times the angle, cosine their angle, right? This one gives us, you just do some math, it gives us 2.732. Of course, it's an irrational number, right? But this is just one of the most important is you understand what is projection, right? What is dot product, sorry. The dot product or inner product, right, is what? Projection of either of this, let's say V1 on V2, but we scale it by V2. Right? Besides just projecting, we also scale it. This scaling is not a problem later in quantum computing because we all have unit vector, okay? And then all the, so this one I say it wrong. I need to have the magnitude. Okay, so let's see if this is the case. Because I say so-called inner product is what? The length, V1 cosine 15, right? So this is the projection, V1 cosine 15. But then I further multiply by the length of V2. That's why I say dot product is projection of V1 on V2 scaled by V2. Is that okay? It's just a way of describing, but the point is you understand what this is, right? Now, if you're going to do this, you will get into trouble because in quantum computing, we deal with the hyperspace. Now I understand what's projection. Yeah, I can measure the angle. I find the dot product and inner product. But what is the projection between the plus state and the minus state? I cannot see it. I cannot feel it. What is the angle? How am I going to measure, right? So there's a definition which is equivalent to this. It is this. I actually should say this is method 1, right? And then another method to do this is just I show you as an example, and you trust me that it works because we don't have time. What you're going to do is this. You will transpose V1. Okay, but what is transpose? Transpose means that you do V1, we call it T. We do a transpose on this. But what is this? Square root 3, 1. Say again, what does it look like now? Becomes a row, right? So if you don't want to mess up, it's very easy. Rotate everything anti-clockwise. Memorize it anti-clockwise. Don't make the mistake. So I rotate it. What does it look like? As he said, it's just a row matrix or row vector. Now maybe you feel very weird or uncomfortable if you did not take linear algebra before. But why do you feel comfortable with going up and down? You just rotate yourself by 90 degrees. The world is the same. Just a way of writing it, right? Now, why we do this? A rule. This is just a rule, a definition. Believe me, okay? Maybe there's some more deeper meaning that I don't know. But that is how it works. You do the transpose, and then do the multiplication, right? Then you just do the multiplication, matrix multiplication. That is why I say I need you to at least know what is matrix multiplication. Then V1 dot V2 is equals to, this is becomes square root 3, 1 times 1, 1. Okay? Anyone know how to do this multiplication? He said it is square root 3 times 1 plus 1 times 1. If you're not familiar with this, now learn it. And it is just a rule, memorize it, like what you learned, how you learn division. You basically, it's like this. The way to do it is just you multiply. One thing is that you rotate it back to column form, and then you merge them together. So square root 3 times 1 plus 1 times 1, matrix multiplication. Now you do the matrix, right? You all have learned matrix multiplication before, right? But you might have forgot. All you need to do is just pick up the rule again. The first element of the row, multiply the first element of the column plus the second element of the row, multiply the second element of the column. And that is, I always forgot also. So that's what I always tell myself. Okay, do this, do this. Okay? And add them together. So what is this? I even forgot, but trust me, it gives you the same result. Square root 3 plus 1, right? This is square root 3 plus 1. Give you about 2.73, right? So they are the same. Right? So why I'm saying so much thing? Basically, most of you can just learn the last one, or even you know this basic thing. But I want to remind you, okay? Now, second method, this is important. I want to warn you now. Right? 3 star. Method 2 is correct only when the basis is orthonormal. You don't know what I'm talking about. We will discuss later. All you need to know is that do not use it without knowing this thing, okay? But luckily, in all the quantum computing framework, we need to use orthonormal basis. Basically, what it means is that this basis vector has to be perpendicular to each other in that sense. If they are not perpendicular to each other, this won't work. It will give you the wrong result. That's all I want to say, right? We'll study what is orthonormal later, but I want to warn you now. Okay?
So the X and
yeah, they are orthonormal. Actually, I should. So what is orthonormal? Example for here, right? You don't need to learn it now, but orthonormal of this basis. This is orthonormal if x hat dot x hat equal to y hat dot y hat equal to 1. First, they are normalized, unit vector, the unit basis, the basis vector and unit. Okay? It's like my 1/8 is unit, my 1,008 is not unit vector. Okay? And x dot y the basis vector equals to 0. As we said, so-called linear inner product is nothing but just what? The projection of one vector to another vector, right? Just the shadow. So if I dot becomes 0, it means we don't have anything in common. Okay? We live in different universe. Okay, any questions? Yeah. Orthonormal means orthogonal plus normalized. So two of them. Yeah, this is orthogonal. Oh no, here. Orthogonal. Okay, and this is normalized. Okay, good point. Yeah. Okay. Now, why I spend so much time to talk something so trivial? Because if you agree with me, then if I tell you, right, just now I show you two-dimensional. If I have a one-dimensional animal, I can only go front and back. I cannot understand this two-dimensional thing. And similarly, we are three-dimensional creature. We live in the space that's three-dimensional. I cannot understand what is 4D or higher dimension, right? But based on the rule we have learned, we can generalize it. Okay? So that is what I want to say. If I have an n-dimensional space, basis vector do I have in n-dimensional space? N, thank you. We have n basis vector. Right? If you forgot, always start with 1. One-dimensional, one basis, right? 1 egg is the basis for the number of egg. 108 means I have 101 egg, right? Okay, maybe I buy a apple and egg, right? Becomes two-dimensional. What I buy today is a two-dimensional space. Let's say we are only allowed to either buy egg or apple. I might go to the supermarket, buy 10 one egg. This is my vector. She might go there to buy 10 one apple, and they might go there to buy 3 one egg and 4 apple. That is the vector space that is spanned by this, the vector space we are talking about. And they span the whole space. The basis vector span the whole space. Every point on this space can be represented by a linear combination of this vector. Okay? So if there's n basis vector, any vector VA, this is just a general vector, can be written as A0, V0 hat plus A1, V1 hat, and too much to write, plus AN minus 1, Vn minus 1 hat. Because I start from 0, so it ends at 0. If this is confusing to you, think about the two-dimensional. A0 times x hat plus B0 times y hat. That's it. And two-dimensional, you go up to 2 minus 1, right? You go all the way to 2 minus 1, which is 1. How about three-dimensional? You have V0, V1, and V2. 3 basis vector. We call it V0, V1, V2, but usually we call it what? X hat, Y hat, and Z hat. It's the same, just a name, right? So this one actually can be written as what? A0, A1, all the way to AN minus 1. You should be very comfortable with this now, right? If you agree how we represent the 2D plane. What is this coefficient talking about? It means I have AN minus 1 of the thank you. of the n minus 1 basis vector. Okay, now it's not just apple and orange. I also buy, let's say, chips or whatever, right? But you need to arrange them well and then follow the order of the bases in the calculation. Similarly, I can have another vector which is B, which can be B0, V0 hat plus B1, V1 hat plus all the way to Bn minus 1, Vn minus 1 hat. Nothing special. AI, BI, I call it AI, BI. What are they? What type of stuff are they? I mean, in program, for V0 is a vector, right? So what are the AI and BI? Coefficient, but what type of thing? What I'm trying to say? Okay, you don't know why I'm asking because it's unclear. Is it a number, a vector, a matrix, or whatever? It's a number. Scalar, very good. Scalar. And what more is that we do complex number. Complex number, of course, includes the real number, right? Okay. So remember now, this is very important in this class. Whenever you see an equation, ask yourself what it is. A scalar, a vector, a matrix, or something even more weird. We will see later. It can be a vector with a matrix as the coefficient later, when you see the polyspin matrix, all this thing. Very interesting. And what I want to tell you in this here, we are going to define the inner product between A and B. A dot B, VA dot VB, as A0 star B0 plus B1 star B1 all the way to AN minus 1 star Bn minus 1. Do you know, anyone can guess what is the meaning of star? Complex conjugate, very good. Where the star means complex conjugate. If you forgot what is complex conjugate, let's remind ourselves. For example, if A equals to 1 plus I, its complex conjugate is 1 minus I. Basically, if you have a complex number, it has a real part and an imaginary part. Its complex conjugate is what? You put a negative sign to the imaginary part. Yes. Thank you. A1 star, my typo. Very good. Okay. Now look at this. I don't know if you see it. This is actually, maybe let me write one more form. I'm too fast. I can write this as summation I equal to 0 to n minus 1 A I star times B I. Do you agree with this? Now I know that when we start going to this equation, you will see this a lot, but nothing to be scared about, right? Don't be afraid of this. All you need to do, just sit down, read, understand each symbol. It say this is a AI star times BI. Okay, I know what is star, complex conjugate. And the I, they are the same. And then you have a summation. You mean, just try it. start with r equal to 0, a0 star times b0 plus r equal to 1, a1 star b1 plus r equal to 2, a2 star b2 plus all the way to r equal to n minus 1, an minus 1 star bn minus 1. That is what exactly happening here, right? And we need to be able to write this, okay, in this class. Also, it's confusing, right? But do you see that how it's related now? I found that this is nothing, okay, but just equals to a0, a1, all the way to an minus 1. Take the transpose and then take the star. Times b0, b1, all the way to bn minus 1. Do you agree? If not clear, let me write it again. This, after transpose, it becomes a0, a1, and then because I need to have this complex conjugate, I put the complex conjugate in, an minus 1, times b0, b1, bn minus 1. Make sense? Yes. Yeah. Yes. Right. They belong to Hilbert space, but even two-dimensional space is a type of Hilbert space. Okay, but you don't need to call the name. It's just a hyperspace belong to it. There may be more mathematical name that I don't know. I'm not well trained in that. Yeah, but that is just a space. Okay, you don't need to really say a 2D or what. But of course you need to say the dimension, right? But what it is actually not that straightforward. Okay, but they all belong to Hilbert space. Okay. How do we do multiplication? Again, I rotate it. Do you see that? A with B0, A1 with B1, AN minus with BN minus 1. Right? Although this looks simple, but you cannot make mistake. Any mistake, you need to do it correct. Okay? What is the difference between this definition and the definition we had earlier? I don't show you the previous slide. What's the difference? Just now we had a two-dimensional inner product, right? What was that? Do you remember how we did that in method 2? Do you remember? This is method 2. What's the difference? Or are they the same? One. Very good. One has the complex conjugate, one does not have, right? But the general definition is that you need to have complex conjugate. Then why I'm correct here? Because it's a real number, right? It's 2D space. So I did not apply complex conjugate, but I know I get the right answer because it's real, right? Because real complex conjugate only flip the sign of the imaginary part. So if it's real, I don't have to do that. Okay? So I'm saying this, I did not do any proof or any important thing, but I just try to guide you so that now you understand what is the inner product, even in hyperspace. Inner product of a 1 trillion dimensional vector is just equal to this. The first one, you take the transpose, followed by complex conjugation, and then you do a regular matrix multiplication. That's why I say you need to learn the rule. Now, how can you do this cosine with the 1 trillion dimensional space? It's not easy, difficult to define, right? And if it's curve or whatever, I don't know. I'm not good enough, but yes. So this is what you need to memorize and not going to make any mistake. Yes. Yes. I will talk about this more later, but basically each of these basis vector need to be normalized. So vi dot vi needs to be 1. And then their inner product needs to be 0. Okay? Yeah. That's why you cannot understand in 3 dimension. Right? You have 10 vector. How can you make all 10 vectors perpendicular to each other in 3 dimension? Right? You cannot. Okay, actually I'm doing this. What is orthonormal basis? Right? This is what we use in quantum computing. And I already talked about this, so we can go a little bit faster. For example, and this is required in quantum computing, okay? Even no one tell you, then you need to assume that. Otherwise, it's not going to work well. For example, I have a basis. Now you see that I put x hat, y hat, z hat. A set of basis vector form a basis, right? X, Y, Z form the basis of this 3D space. Now, since you already know how to do 1 trillion dimension, I'm sure that you are okay if I tell you this is also a basis, right? Spin up and spin down form a set of bases which span the space of the spin. Are you comfortable with this? I already told you I was able to form a basis with 1 egg and 1 apple and span the space of any purchase of egg and apple. Yeah. That is the physics. You just trust me. That becomes a linear combination. Exactly, right? It's just like why in 3D we only limit to 3 bases. Right? You're just like saying that any vector can be in any dimension. But we can decompose it. All of them can be represented as a linear combination of these 3 basis vectors. Same for spin.
So I guess if you had 3 dimensional,
Something wrong. You don't have 3-dimensional. I mean, in this, when I'm talking electronic spin, there are other spin. For example, the quark color. You have a color. Color. I mean, just the up down the quark, right? How they combine, they have this color. Instead of spin or charge, they have extra physical quantity. We call it color. Then it has 3 bases. I think I'm right. I hope that I'm right. Red, green, blue. There's not really red, not really green, not really blue. We just call it red, green, blue. Because there's no color. You cannot see color for object lab smaller than the proton, right? But it forms a space that has the basis that is red, green, blue. So you have 3 basis vector. I hope I'm correct. I really forgot all this physics. But I just want you to understand, if you agree 1 egg and 1 apple is a valid basis, you don't feel weird about that, right? I told you I buy 100 apple and 2 egg today. That is 102,2. That is my vector, what I buy from the supermarket today. And the basis 1 egg, 1 apple. Then I hope that you don't feel it's weird that I tell you there's something called spin up and down. Maybe you never eaten egg and apple before. Isn't that you feel also very weird? You told me something called apple, which is sweet, and egg, which is raw. You need to cook in order to taste something, right? Think about that, okay? So this form a basis, right? And in general, I need to be careful. You can have the basis vector from 0, 1, all the way to this. What is the dimension of this basis? N-dimensional, right? Remember, we start with 0. So if AI dot, I changed the symbol. If Vi dot Vj equals to 1 when I equal to j, equal to 0 when I not equal to j, then this is called, then this is an orthonormal basis. Okay, the basis spanned by me is orthonormal. For example, I can claim that one egg and one apple, they don't have common part. Depends on how you say it. Okay, the colors are not common, the tastes are not common. Yes, question? Okay, state is vector. Okay, so basis state is basis vector. Okay, state is vector. Okay, every physical system, they are in a certain state, and we represent it by a vector. The state can be very complicated, so I can have 1 trillion parameter to describe it. It's a 1 trillion dimensional vector. Some state can be very simple, like spin. I only need 2 parameters to describe it. Then it's a 2-dimensional vector, but it's the state of the spin of the electron. Okay, very good question. Then this is overall. I take this opportunity to tell you something. Delta ij, I want you to memorize this. This is just a symbol. It's exactly the same. It's just saying that when I equal to j, it is 0. It is 1. When I not equal to j, it is 0. This is called Kronecker delta. You will see that very often and very useful. Okay. If you have not learned that before, right? Let's just look at an example. I think the best is everything we go through some simple numerical example. For example, I have this one, which you already know. This is x, this is y, right? How do I represent this basis state in column form? First of all, how many basis states does it have? 2. What are they? What do we call them? X hat and y hat, right? Now, I want to represent x hat in column. Yeah, although basis state, we don't need to describe it, but still basis state by itself, so special, is still a member of the state of the vector in the vector space, right? So they should have an identity. They should have a representation. How do we represent it? In column form. This is 2-dimensional, so I only need 2 numbers. How do I represent it?
So 1.
1, 0. This is very important. Sometimes it's so simple that we dare not to write it. Why I say this is correct? Because it has 1 unit of the first basis state. It has 0 units of the second basis state. Right? That's consistent with what I've been talking about, right? That's the meaning of the column form. The first is the 1 unit of the x hat. Second unit, you have 0 units of y hat. So what is y hat? 0, 1. Very easy. Okay, so let's check. What is x hat dot x hat? Let's just repeat what we learned. You need to do transpose. Yes? What is this? 1 times 1 plus 0 times 0, right? Just matrix multiplication. So this is 1. Similarly, you will get the same thing for y hat dot y hat. So it is normalized or not, this system? Yeah, normalized, because all the unit vector, the basis vector has unit length. Okay? How about x dot y? You said 0, right? But let's be careful. 1, 0, right? Because I need to do the transpose and then complex conjugate for the first one. For the second one, what is this? 0, 1. Let's do the multiplication. 1 times 0 plus 0 times 1. Everyone follow how I do this? 1 times 1 times 0 plus 0 times 1. Okay? What is this? 0. So they are orthogonal. I know this is simple, but in the future, when you see something very complicated, think about the basic thing and then go back. Okay? Question?
The preceding slide, vector or a state in terms of its basis states.
Yes.
It was vector this time x, this time y.
Yeah. Right. Right.
Here, the basis state itself
Yes.
equals to and then
Correct.
something else.
But still, basis state or basis vector is just a state and it's just a vector. So I'm just doing the same thing. What I'm trying to write here is this. X equals to 1x plus 0y. That is what I'm trying to do. Okay? It's still correct. It's just for people who don't know what we're doing, say, you are not really telling me what's x hat. They really want to know what is x hat, but you say, x hat is 1x hat. You're so pissed off, right? The professor asked you to answer the question in exam. Find cosine 54. The answer is cosine 54. Actually, you are right? I don't know why they will take away your point, right? In some sense, you can sue him or her, right? So, unfortunately, that is this, but that is correct. It's still the same definition. Very good question. Okay. Okay, so good. Now we know all these things. We are good at vector space now. Now our calculation is very troublesome if we continue to do this. We need to learn the bracket notation by Dirac. Okay, this is a very useful notation, but it's easy. I introduced in the introduction already, right? And I've been trying to use it. Let's start with something called cat. Okay, later you'll know why it's called bracket. Okay, for vector A, now I decided to write it in this way. I already showed you that anything I put in this cat is just a name. Okay, it's just a name. So I can really call this A. You don't like it, but I'm not confusing you. Think about that. I'm just put some symbol there. If we have some agreement before, I'm not confusing you. A means vector A. And if I want to do some encryption with you, like the kids, I just want to call it apple. This vector is apple. Yeah.
So this
The cat. Okay, yeah. Actually, maybe, but I don't know. The whole thing is called cat. But I don't know if there's any name for that. Yeah, it's just called it cat. Okay. Well, what if I do this? I point at that vector and say this vector. Is this okay? No problem, right? As long as I'm clear, if I don't point at that vector and say this vector, that's not then I have a problem, right? So I want you to feel the power first of all, just a name. We can write it in this way. If that is the case, how do you write A equals to VB plus VC? I have two vectors, VB plus VC equal to A. That's nothing special. You know that before. How do I write in cat? Anyone want to volunteer? Actually, it's difficult to say, right? If just put in cat, we call it A equals to B plus C. Okay? Up to you. You can write VA, VB, VC as long as it's not confusing. That's fine. Okay, good. Well, we also have done this before, right? We know that we can scale the vector like this. What is C? Can someone tell me what is C? VA and VB are vector. What is C again? Scalar. Thank you. Keep asking yourself. It's just a number at Best is just a complex number. I can write it in this way also. A equal to C times B. Okay, start getting used to this notation. You understand the one inside the cat is a vector. Don't touch it. It's a name. You cannot change the name randomly. Okay, unless you know what you are doing. This is called cat. Now, this is not interesting. It's just a new notation. But Dirac came up with something called bra. And after this, you know why they are causal. It says that what is a bra? It's the dual space of the cat space. Now, your vector form a space. That's okay. Like in this real world, 3D space, okay? Now I stand in front of the mirror. I see everything repeated in the mirror, except that the orientation is shift. But there is another space, right? You say it's a virtual, but who knows? Maybe that guy in the mirror say that I'm virtual. We are just not intelligent enough to really understand actually maybe inside the mirror is a real stuff. We are virtual. Who knows, right? But that's just kidding. But it's just like this. Every vector has a space. You mathematically can construct another space, which is a bra space. But this space is corresponding to that space. There's some relationship between this dual space, this bra space, and the cat space. That's why we say they are dual. Okay, they come together. How do you construct the corresponding vector? We write it in this way. A is the bra version of cat A. It basically is just saying that the mirror, the image I see myself inside the mirror is the image of myself. You see that there's some difference, right? My left and right got flipped, right? I raise my left hand, the image raised his right hand, right? This is also a vector space. It obeys everything related to the vector. But what we care the most is how do we construct the vector? We construct by, can you guess? Actually, you cannot guess. It's related to inner product. Which, yes, transpose plus compress conjugate. Right? The easiest way is to take a look at an example. Okay? For example, if A, VA equals to AB. I know I have 2A, but it should not be confusing. What is the component of the first basis vector? What's the magnitude of the first basis vector? A. Although the vector called VA, I know, but I try to confuse you. This is the purpose. A is just a variable, a number. And it has B components of the second basis. Okay? What is its bra version? Transpose. Compress conjugate. Okay? What is the inner product? Let me don't do this. Let's do this later, right? Now, let's look at another example. Let's look at an example. I have another vector, VA times VA equals to ABC. What is the dimension of this vector? Which space does it reside? Three-dimensional. But it can be compressed coefficient, not our real 3D space. B equals to, let me call it E, F, G. What is the inner product between A and B? Say again. Plus. Now, if you talk about the coefficient, then don't use this star, not plus. Or you mean plus, okay. We need to take the complex conjugate, right? So it's A star times E plus B star times F plus C star times G, right? If I write it in the column and matrix form, what does it look like? It is like this, right? A star, B star, C star times E, F, G. Is this okay? But what is this one? In bracket notation, what is this one? This is just the bra of A. Very good. And how about this one, E, F, G? Still just the cat of B, right? And let me just merge them together. So it turns out the inner product of any product is just the bracket of them. And that's why now, do you understand why it's called bracket? Anyone see that? It's a what? A pun? Explain more. My English is not good. Yeah, play on the word. Yes, exactly. But can you exactly say how it is a pun?
The question is becoming more confusing because it's like a joke. Separate two words have two separate notations. Then when they come together, you get that rapid notation.
Yes. Okay, you go very deep. Yes, exactly. But what I'm saying is, because this is a bracket, and he removed the C, bracket. That's it. Okay? So in this case, I hope when you think about bra, you know that, okay, it is this direction. Think about cat is another direction. Now here, just very important, you see that very handy. If I want to find the inner product of the vector, it is just the bracket of these two. Yeah.
Is it A, B, or B something?
Can you say where? Yeah. Okay, yes. Okay, so I'm not consistent, but on the other hand, I hope that you find it confusing, but you know that it is not confusing. Because A, B, C here are just number. So there's no point for me to put a number in there because it's a vector, right? There's no relationship. And for VA, sometimes I like to write as A, sometimes I like to write as VA. Because it's just a writing. It's no difference, but now I try to write Japanese or Korean or English. But yes, it is confusing, but I hope that you will figure out that this is not, while it's confusing, it is not really giving you the wrong result. I don't know if you understand what I say, maybe I'm wrong, but first of all, it's confusing. To be consistent, I better write VA, VB, right? VA, VB, okay? But again, I can call VAA, VBB, right? VA as A, VB as B. It makes, but again, if you think a little bit more, yeah, this A is just a coefficient. What is the meaning? Let's say this is 5. What is the meaning of bracket 5? No, it has no meaning. Just unless I know which vector you're referring to for 5, right? Yeah, okay, I agree with you, it's confusing, but I hope that later you also agree mine is not completely confusing in some sense. But you're right, definitely right, this is confusing. I get that you point out. Question?
So
When it's a broad notation, you don't change. This is just a name. Again, anything inside the bracket is just a name. You don't change anything. But when you try to represent it mathematically, then you have complex conjugate, and also you need to rotate it to a row vector. Right? Do you see this? This is VA, I put AB. This is VA bra, I put A star, B star. Right? I don't need to put star here. Don't put that. Because when you put that, then you are going to mess up. People will think that you take the complex coefficient of the cat space, then you go to bra space. Cat VA, yes. Where is cat VA? This one? I'm talking about I have a vector VA has 3 components ABC. This is a new example. Now I go to a 3-dimensional example. Make sense? Yeah. So I think that this is the most confusing one. Once it is clear, then you can move forward. Right? Any other question? If not clear, let me know. You're helping others by asking questions. Okay, email me if you have questions, right? So we are done with this vector and state, right? We will keep repeating. Now, so what is a vector? Let me say it again. Every state, right, of a physical system is a vector. Right? I mentioned many times already, but hope that now you are okay with it. Any state, right? Everyone in this classroom can be represented by, altogether represented by one physical vector at this moment. Okay? So that's okay. That's why we learn vector, right? And every state, and now we know that it is also a vector, is a superposition. My pen is not working well. Or I call it linear combination of the basis state or basis vector, right, with S. Is that okay? We have been emphasizing this, right? You need to accept it. What do I mean? If I now tell you, you have not learned any physics before, for example, there is something called spin. Something called spin of an electron. Don't even imagine it's spinning. There's no such thing. It's just a state. Electron does not spin like what you're thinking, not physically spin, right? A spin, but it has a state. It's going to be the linear combination of spin up plus spin down. Or, as I said, you doesn't have to draw it. You don't like drawing. We just call it 0 and 1. Well, some people like to say, hey, this is a plus spin corresponding to the eigenvalue of plus, the other corresponding to minus. All this one saying is that the spin eigenvalue half, the state corresponds to the spin eigenvalue half. By looking at this, if you never talk to that person, you don't read what they're talking about, of course you don't know what they're talking about. But if you know that, this is not ambiguous. You're just talking about the basis state, I call it half. I can call anything, right? I don't have to call it 1/8. I can call it 2/2 as a basis state. 2/2. I just want to play the trick. Right? So be very comfortable about this. Right? If you agree with me, today all the people who buy egg and apple from the supermarket, what they bought from the vector space, then you should feel comfortable that the basis vector are 1 egg and 1 apple. Right? My mom got 5 apple and 5 egg this morning. So the vector, I can ask how much you bought. She said 5, 5. I understand what she's talking about. 5 egg and 5 apple, 5, 5. I saved my time. If you're okay with that, then why is so difficult to understand this one? Except that you don't know what is spin. But maybe you also don't know what is egg, what is apple. I think apple and egg are more complicated than spin, in some sense, right? So I hope you are comfortable with this, then you can move forward. Of coefficient, we talk about superposition, right? We actually talk about meaning of coefficient already, but what does it mean, right? Let's have a more mathematical description. So for general states, I can write it as V equals to A0 V0 plus A1 V1 all the way to AN minus 1 Vn minus 1. A very long, but you should be very comfortable with this because, well, this is just a Dirac Braket notation. So this is a vector. Even I don't know what it is, I know it is a vector. That is the first thing you need to recognize. There is a linear combination of many vectors, yes. And then now I tell you, someone need to tell you, V0, V1 are the basis vector. Okay, then you understand. Okay, A0 to AN minus 1 are just complex numbers. So a linear complex number of all these basis vectors. Should it be 1, 2, or 1 trillion? Doesn't matter. Done. So when I do the measurement, as I told you earlier, and you need to accept it, right? This is one way of the interpretation of quantum mechanics. When we do measurement, very easy. Measurement is very difficult to formulate, but to understand is very easy. To accept it is very easy. It will collapse to one of the basis state. So I measure it. So what does it mean? The V, such a big V, it will become either V0 or V1 or Vn minus 1. Any of them. Like the spinning coin, stop it, will be either head or tail. I don't know where you will go, right? It's statistical. But I do know one thing. It means it collapses to Vi, right? With the probability of AI magnitude square, which is also AI star times AI. This one you need to trust me, right? You just go back to do some math. The magnitude of a complex number square is just its complex conjugate times itself, right? So let's look at an example. And all this is just you accept it and trust it and memorize this important thing. For example, if AI equals to, now here actually I'm a little, let me do this, square root 2 plus I divided by square root 2. I think I better do this, right? So this actually, now this is confusing. This I, let me call it AJ. Or let me just don't call it, let's call it A0, for example. Okay? So what is A0 star? Anyone want to tell me? Minus I squared 2, right? So you get A0 star times A0 equals to 1 over square root 2 minus I divided by square root 2 times 1 over square root 2 plus I divided by square root 2, which is equal to 1 over 2 minus I squared divided by 2. What is I squared? Minus 1. So this equal to half plus half equal to 1. Turn out that this wave function has everything, only has this V0, because the measurement probability is 1. But here, just to show you how to do the calculation. If you don't trust me, then now try to do AI magnitude square. You will get the same thing. Okay? So time's up, we will stop here. Any question, just let me know.